Hello everyone, in this video I will go over my solution for the problem named Weight the Tree taken from today's Codeforces round. This problem is an excellent problem which teaches us the applications of tree dynamic programming in trees where we are minimizing two values. We are maximizing one quantity and we are minimizing another quantity simultaneously in the dynamic programming state. So this problem teaches you how to do this and how we can store pairs of integers in our DP and how we can do that on a tree and not just a normal array. So in this problem, we are basically given a tree of n vertices with the nodes numbered from 1 to n, and this is the definition of a tree. And for each I from 1 to n, we need to assign a weight to the ith node, and the ith node is called good if its weight is equal to the sum of the weights of all its adjacent nodes, which basically means that the weight of a good node will be equal to the weight of the adjacent nodes, the sum of the weights of all the adjacent nodes, which basically includes the parent node and the children. If you wrote the tree at node 1, so immediately you should think about rooting the tree at node 1, and you should think about the weight of the node is the sum of the weights of the children and the weight of the parent node. Now we need to maximize the number of good nodes in the tree, and we also need to minimize the sum of the weights in the tree. So first we need to maximize the number of good nodes, and second we need to minimize the sum of the weights in the tree. So let's take an example, which is the first sample. The tree is basically 1 to 2, 2 to 3 and 2 to 4, and since we always root the tree at node 1, if you have seen the previous tree DP lectures, you will realize that we always need to root the tree at node 1, and we always need to figure out the DP state and the recurrence and the base cases. So first let's start out by noting that whenever we have a node which is a good node, then the weight of the good node will be equal to the weight. So let's say u is a good node, then the weight of u will be equal to the sum of the weight of v, where v is a child of u, plus the weight of the parent of u. So this is what the weight of the good node u will be, and the weight of a bad node will be equal to, so this is one possibility, or the weight of the node which is bad will just be equal to some number. So let's, for simplicity, say that since we want to minimize the sum of the weights, and the weights can be between 1 and 10 power of 9, that's why if this is a bad node, if u is a bad node, so let's say u is a bad node, then in that case we assign the weight of u to be equal to 1, and the reason why we assign the weight of u to be equal to 1 is so that the sum of all the weights in the whole tree is minimized. Now let's make an observation. We know that the weights of bad nodes are equal to 1 because of this minimizing the total sum, and that's why let's try to find out the weight of good nodes. So the key idea is that whenever you have a good node, so let's say you chose 2 to be a good node, so let's say that this is a good node, then in that case, since the sum of the weights of 1, 4 and 3 should be equal to the weight of 2, we need to ensure that the weight of 2 is equal to weight of 1 plus weight of 3 plus weight of 4 if 2 is a good node, and this means that the weight of 2 will be strictly greater than all these three quantities, and this means that weight of 1, weight of 2, this basically means that 1, 3 and 4 are all bad nodes. 1, 3, 4 are all bad nodes, and this is because if you consider 1, 3 and 4 individually, their weights can never be equal to the sum of the weights of the adjacent children. So if you consider the node 1, then the weight of 1 cannot be equal to weight of 2 because the weight of 1 is strictly less than the weight of 2, and similarly the weight of 3 cannot be equal to weight of 2, and weight of 4 cannot be equal to weight of 2 because they are all less than the weight of 2. That's why all adjacent nodes to a good node will be bad. So all nodes adjacent to a good node will be bad, and that's our first observation. So actually the first observation is this: if you consider bad nodes, then the weight of the bad node should be equal to 1. And the second observation is all nodes adjacent to good nodes should be bad nodes. And this basically means that if you consider good nodes, then we know that since all nodes adjacent to good nodes are bad, this basically means that the weight of a good node will be equal to the sum of the weights of all bad nodes which are adjacent to the good node, and which will basically be equal to the number of adjacent nodes into 1, because each bad node has a weight of 1, and we know that a good node has a weight equal to the sum of the weights of all the nodes adjacent to it. That's why the weight of the good node is number of nodes adjacent to it. And this is the second observation. So these two observations are enough to come up with the solution for this problem. So I encourage you to pause the video if you have not figured out these two observations. Take some time to understand why exactly these are true, and then you can basically think about how we can use these two observations in order to solve the problem using tree dynamic programming. So the key idea for tree dynamic programming is that we will use two DP arrays. The DP arrays which we will use are going to be DP0 of u and DP1 of u. DP0 of u will store two values. The first value which it will store is the maximum sum, the maximum number of good nodes, and the minimum sum, of all the weights if you are considering the subtree of u, in the subtree of u, and with u being a bad node. So first note that we always define the tree dynamic programming with respect to the subtree. You could see that from the previous problems as well in this tree DP playlist. That's why we will always consider the subtree of u, so this should not be anything of a surprise to you. And the second thing, which is the only thing which changes, is the definition. So the definition is basically going to store two values. One is the number of good nodes, and second is the min sum of all the weights if u is a bad node, if u is bad. And the second value, which basically is dp1 of u. So dp1 of u stores the exact same thing. It stores the exact same thing. We are trying to maximize the number of good nodes because that's what the problem statement is asking us, and we are also trying to minimize the sum of the weights, and we are also considering only the subtree of u. So those parameters remain the same in this recursive method, in this recursive function, in this dp state. However, the only thing which changes is that in this case u was bad. However, in this case u will be good. So in the previous case u was bad, and in this case u will be good. So this 0 basically signifies that u is not a good node, and 1 basically signifies that u is a good node. That's why we use 0 and 1 for the values, for the dp variable names. Now let's try to use this statement in order to find the recursion and in order to find the base cases by using these two observations as well. So in order to find the recurrence, let's use the method for finding the recurrence, which is considering a node u and considering its k children in the subtree of node u. And let's try to find out the two recurrences. So let's first start with dp1 of u because that is a bit easier to work with, because from our first observation we know that the bad nodes, or from a second observation we know that all nodes adjacent to good nodes are bad, and this basically means that if we consider u to be a good node, which is dp1, then in that case we know that all the adjacent nodes are bad nodes. So that's why we know that the weight of node u, so in this case the weight of node u will be equal to the number of adjacent nodes. So we can use adjacency list. So it will just be the size of the adjacency list. So adjacency list of u dot size will give the weight, which is actually the second quantity, and the first quantity will be the number of good nodes. So the number of good nodes will actually be initialized to, so number of good nodes will be initialized to 1, and the weight will be initialized to the size of the adjacency list. Then we can compute the recurrence. So this will be the initial values. Then we can compute the recurrence by using the fact that for every adjacent node, we will just sum up the value of dp0 of v, where v goes for each of the children. So you could write this mathematically, and this is the recurrence because we know that all adjacent nodes to node u will be bad nodes, so that's why we use a dp0, and we sum up them because we know that the number of good nodes will be summed up and the weights will also be summed up. That's the reason behind why we sum up the values. Now let's consider the case. So this is the case when u is a good node, and let's consider the case when u is a bad node. So when u is a bad node, we know that the weight of u will be equal to 1 and the number of good nodes will be initialized to 0. So this is our base case. The one which I've written in brackets is the base case, and now the recurrence will basically be dp0 of u will be increased by the maximum of two quantities. I mean, okay, so over here there's a bit of a trick which is involved. In order to find dp0 of u, you will need to realize that there are two possibilities. For each adjacent node vi, so let's say we are considering some random child vi, then for that adjacent node vi, it can either be a good node or a bad node, because u is a bad node. If u was a good node, then we know for sure vi has to be a bad node. However, in this case, when u is a bad node, vi can be a good node or a bad node, and that's why we need to use the dp to consider both possibilities. So that's why we need to use the dp of u will be increased by, so dp of u will be increased by two cases. There are two cases. So let's say that vi was good. So let's consider two cases. If vi was good and if vi was bad. If vi was good, then we would be considering dp1 of vi. Otherwise, we'll be considering dp0 of vi. However, if you just sum up the maximum of these two quantities, you will get something wrong. The reason being, you need to realize what the definition of the dp state is. The dp state is storing two quantities. It is storing the maximum number of good nodes, so that is fine. If you take the maximum, you are always maximizing the number of good nodes. However, it is also storing the minimum sum of the weights, and since it's storing the minimum sum of the weights, if you take the maximum, it won't work. You need to take the minimum. So how do we do both of these things? So one possible way, there are two possible approaches to solve this subproblem. One possible approach, one fix. So fix number one is to manually check. Fix number one, use some if-else statements, and you can basically check. So if dp0 of this v is the current v, if dp0 of that v dot first, which basically represents the number of good nodes, if that is strictly greater than dp1 of v dot first, then you'll obviously prefer the dp0 of v. So we will increase dp1 of u by we'll increase dp0 of u by dp0 of v, because we are considering we are finding out dp0 of u and we are increasing it by dp0 of v. Otherwise, if dp0 of v dot first is strictly less than dp1 of v dot first, then in this case dp1 is better. dp1 gives us more good nodes, and that's why we will go with dp1 to both the quantities. And the final case will be if else we know that both the quantities are the same. That's why we need to compare the second quantities, and in this case we want to minimize the second quantity. That's why if the second quantity is lesser, you can then just basically add the second quantity. So if dp0 of v dot second quantity is less than dp1 of v dot second quantity, then in that case you add dp0 because you want to minimize the second quantity if the first quantity is the same. So that this is what you will do. And sorry if I'm making some small mistakes over here, like interchanging dp0 and dp1, but you should be able to do this without any hesitation. You should know that there are basically four cases. The first case is when dp0 of v dot first is greater than dp1 of v dot first. So dp0 is greater than dp1 for the first quantity. In that case we will take dp0 of v. However, if dp0 is less than dp1 for the first quantity, then we will take dp1. Otherwise, if their first quantities are the same, then you will compare the second quantities and you will take whichever one has a smaller second quantity. So you can just use a lot of if-else statements and do this. However, this code becomes very long. It's almost 8 lines, which is not needed. You can reduce this to just 2 lines if you use the second fix. And the second fix is a normal trick which is useful, and it helps simplify the code. And let's say you interchange dp0 and dp1 somewhere, you won't have to debug as much. With longer code you need to debug more, so that's a problem, especially in the contest. That's why the fix number 2 is to modify the dp. So the best way to modify the dp is to store not the maximum number of the maximum sum, I mean to not store the minimum sum, but to store the negative value of the minimum sum. So if you store the negative value of the minimum sum, then when you like if you store this for both dp0 and dp1, then when you take the maximum, so over here when you take the maximum, you're ensuring two things happen. You're ensuring that the number of good nodes is maximized, and the minimum sum, the negative value of the minimum sum is maximized. And this basically means that the positive value of the minimum sum will be minimized, and that's why the minimum sum will be minimized, and that's the desired objective. So this is the best fix, which is to store these two quantities instead of using 4 if-else statements, and then it just becomes 2 lines code, and it greatly simplifies the logic, I mean the implementation. So the main part of the logic remains the same, where the base cases are this and the recurrence is this, and you can fix the recurrence by either using fix number 1 or fix number 2. Now I'll be showing the implementation where I implement fix number 2, because that is a better fix. And if you had any doubts in the recurrence so far, or in the base case or in the DP, just leave them in the comments down below. And now I'll show you the code. So in the code, there are 2 parts to the code. The first part is doing the DP. The second part is actually printing out the actual values, printing out the weights. I have not mentioned this in the logic because you should be able to figure out how you can print the weights by basically reversing the DP. I'll show that in the implementation, but you should be sufficiently good in DP and should have practiced some simple DP problems in order to understand how you can go backwards. But anyways, I'll explain that in the implementation. So let's look at the implementation details. I use adjacency list representation, and I use 2 DP values. I use long for simplicity, I mean for overflow errors, so that overflow errors don't happen. And then I basically, this is used second part. So this is used in the second part where used of u stores whether or not the weight, whether or not the node u is good. So if used of true, if taken of true is taken of u is true, then node u is good, otherwise node u is bad. Initially all the nodes are bad, and then we keep assigning them as good as and when we take them. And vector int answer stores the final weights, and we know that the final weights are going to be either 1 or they are going to be adjacency list of I dot size. And um, we are basically doing the DP to figure out which of these two quantities are going to be stored. If U is a good node, then you know that you need to use adjacency list of U dot size, and if U is a bad node, then you need to know that U is going to be 1. The answer of U is going to be 1, and this is the two DP tables. And now let's look at the DP. So in the depth first search where I do the tree DP, I use the base cases. So the base case is like as I showed you in the whiteboard, DP U of 0 will be equal to 1, and DP 0 of U will be equal to 0, and DP 1 of U will be equal to 1, and the sum of the weights will be -1 and minus the size of the adjacency list, because we know that -1 will be the number of good nodes will be 1, and the number of good nodes the weight will be 1, and the weight will be adjacency list of U dot size respectively. So you should pause the video and see why the base cases are true and why I'm negating them. The reason for negating them is because, as I mentioned, we are using fix number 2. So we use a fix. Fix is to store the negative of the min sum of all weights, so that we don't have to use a lot of if-else statements. And now let's look at the recurrence. So in the recurrence, for each adjacent node, if the node is a child, then we will basically consider the cases. So first, dp1 of u will increase by dp0 of u. So this basically means that dp1 of u plus equals to dp0 of v, and that's the first part, that's dp1. Now for dp0 of u will be increased by dp1 by the maximum of two quantities, dp1 of v and dp0 of v. So if dp1 of v is greater than dp0 of v, we will take dp1, otherwise we will take dp0, and this is the recurrence, this is the fix. And the reason why we can just take the maximum is because we are storing the negative of the minimum, and this basically means that maximizing the negative of the minimum, will minimize the quantity. That's the trick which we use, and that's why we can just store the negative and maximize that. So that's what we do over here, and this is the DP. The second part, which is mostly implementation, is only implementation, so you should know how to do that, because this is like problem D level, and this is just implementing the DP in the reverse order. So I'll show you the code once I show you the main method. So in the main method, there is one border case which you should take care of. The border case is when n is equal to 2. So when n is equal to 2, the reason why our logic doesn't work is because the second observation is false. The second observation is false when n is equal to 2. And the reason why this is true is because when n is equal to 2, there are just two nodes in the tree, and both will actually be assigned weights of 1. So that's why this is just a border case which you need to take care of. And in general, the second observation works, so don't get panicked if you find this as a border case, even though n is like 2, which is comparatively big. So once you have taken care of this border case, the DP works, and I just call the DP on the first node. So this does the DFS and the DP. And now, in order to print the final answer, we print the maximum value of the two quantities. So if dp0 of 1 is greater than dp1 of 1, we will print that. Otherwise, we will print dp1. So in case dp0 is greater than dp1, we will print dp0, and otherwise we will print dp1. And when we print dp1, we know that the node 1 is taken, so that's why we mark taken of 1 to be true. And now let's go to the implementation details for the reverse DP. So in the reverse DP, if the parent is taken, or dp0 of u is better than dp1 of u, then in this case we take 0. 0 is better. So this basically means that u is a bad node, and that's what we do. In case the parent is a good node, this means that you should be a bad node. However, if the parent is a good node and dp0 is better than dp1, then we take dp0. So in both the cases we need to take dp0, which basically means that u is assigned a bad node. In the other case, u is a good node, and that's what we do. We mark taken of u to be 1, and we mark the answer of u to be the size of the adjacency list, which is the good node weight. And now let's look at the DFS. Then we just call DFS on all the adjacent nodes, and in this way we are always visiting the parents first, and then we are calling the DFS on the children. That's why this all of this is valid. And now let's look at the main part. In the main part, once we assign the node 1 to be either a good or bad node, then we call the depth first search on all the adjacent nodes to node 1, and then we basically do the implementation. And after we do the implementation, so another way to write this is to just write it over here in one line. So this is cleaner, and after we call the DFS, after we have assigned the node 1 to be either good or bad, we call the DFS, and then we print the values, and these values represent the weights, and this is the full code. So if you had any doubts in this implementation, the implementation is a bit long, but hopefully the idea is crystal clear. So if you have any doubt along any of the steps, do leave them in the comments down below, and if you like this video, don't forget to give it a thumbs up. Thank you.